This is question 6 from 1988 International Math Olympiad, and it is believed to be the hardest ever question in the history of International Math Olympiad. I have no idea absolutely what's going on until I Googled the answer. So here I'm gonna try and go through the proof combined with my own understanding. So basically what the question is asking is that consider this left-hand expression, right? A, B, both positive integers. There are two possible outcomes, right? So we have integer over integer, right? Only two possible outcomes. Either it's going to be an integer or a fraction that cannot be simplified down to an integer, right? If it turns out to be an unsimplifiable fraction, then we're not interested. We're going to just leave it as it is. We're only interested in the case of the expression turning out to be an integer, k. Right, we're going to prove in that case k must be a perfect square. So by trial and error, we found that when a is equal to 8, b is equal to 2, right, then we have the following left-hand side is equal to 8 squared plus 2 squared over 1 plus 8 times 2. Essentially 64 plus 4, 68 over 17 equal to 4. Indeed, perfect square, no problem. And consider the case where if A and B are equal to each other, right? In this case, what's going to happen, right? So left-hand side equals twice of A squared over 1 plus A squared equal to k. If it turns out to be an integer, what's going to happen now is that twice of A squared is equal to k plus ka squared. Right? In other words, move ka squared to the other side. We have 2a squared minus ka squared equal to k. In other words, extract out a squared, we have a squared times quantity 2 times minus k is equal to k, where k is strictly positive, right? So A, B strictly positive, 1 strictly positive, right? Strictly positive. So in other words, because A squared is strictly positive, therefore 2 minus k has to be strictly positive, which means k must be strictly less than 2 at the same time strictly positive, which means in this case k has to be exactly 1, right? If that's the case. Now, consider, so without loss of generality, we can just assume that A is bigger than B. B is bigger than 0, right? Without loss of generality. The reason is because this expression is essentially symmetrical. If we just write b squared plus a squared over 1 plus ba, it's the same thing, right? So we can do this assumption. Now, so under this assumption, what's going to happen is that we're going to have to rearrange that expression, right? A squared plus b squared equal to k plus kba, right? Just multiply the bottom over here. So now I'm treating A as a solution to the quadratic equation where I can write leading term to be A squared minus kba plus b squared minus k equal to 0, right? So in other words, I have the following quadratic equation, which is x squared minus kbx plus b squared minus k equal to 0, right? So 0 less than b, b less than a in this case, right? So this quadratic equation, we clearly have a real solution, that is a, right? Because a makes this equation true, right? Derived from previously from this expression, right? So conclusion, so a is a real root, which means our discriminant has to be non-negative, right? So in other words, we have one more solution, another real solution called A1. Now the question is that I want to know the sign of A1. Is it positive, negative? Is it bigger than A, smaller than A? Right. Here's my claim. That A1 is very small. Right? First of all, A1 is smaller than B. Right? If A1 was bigger than or equal to B, in this case, what's going to happen? First, let's have a look at the Vieta's formula. Right? So the sum of the two roots is equal to A plus A1 equal to KB. Right? The product of the two roots is equal to B squared minus K. Right? What's going to happen now is that if A1 was bigger than or equal to B, in this case, we can just express A1 as the following. B squared minus K over A, right? If it were bigger than or equal to B, right? If it were bigger than or equal to B, in that case, what do I have? I have B squared minus K bigger than or equal to AB. Right? In other words, AB bigger than A. B squared minus AB bigger than or equal to K. Extract B minus A. B minus A bigger than or equal to K. Right? Since following our assumption, right, B is smaller than A. B is smaller than A. B minus A is negative. Negative times positive turns out to be negative. Negative number is now bigger than or equal to than a strictly positive number. Cannot happen. Contradiction. Right? So my assumption is wrong. Right? So A1 cannot be bigger than or equal to B. In other words, my claim is right. A1 is really strictly smaller than B. So far, what I've done is that I've shown that when A is equal to 8, B is equal to 2, then our expression is indeed a perfect square. I've also shown that if A is equal to B, then K must be equal to 1. And I've also shown that for this quadratic equation, under this assumption, A being a real root, as I've proven, and also A1 being another root, A1 has to be strictly less than B. Now, again, I'm going to show that A1 is at the same time non-negative. Right? So here's another claim. A1, non-negative. If otherwise, if A1, let's say it's negative, what's going to happen? Right? So if A1 was negative, let me just have a look at the original expression. Right? So instead of using the exact formula for calculating the root, we're going to again just straight away plug A1 into here. It'll be easier, right? So under that case, my original expression should equal to A1 squared plus B squared. and minus k b a1 minus k. Right, supposed to be equal to 0, but I'll show that it cannot equal to 0 under this case. The reason is because a1 squared plus b squared already is strictly positive. Right? And also at the same time, this expression, right? This expression is equal to, just extract k out, right? Minus ba1 minus 1. Right? So what's going to happen now is that since a1 is strictly negative now, so therefore negative a1 is strictly positive, which means greater than or equal to 1. In other words, if I multiply by b on both sides, negative ba1 is, b is positive, so still the same direction, larger than or equal to b. So in other words, minus ba1 minus 1 is larger than or equal to b minus 1, right? So the whole thing is larger than or equal to, k is also positive, so still same direction, k times b minus 1, like I said. At the same time, b is strictly positive, right? b is greater than or equal to 1, so b minus 1 is non-negative, right? So larger than or equal to 0. Right, so turns out to be this is non-negative, right? Plus this strictly positive, so it has to be strictly positive. No way it can be 0, so that's a contradiction. Right, so meaning a1 cannot be negative. So a1 has to be, could a1 be equal to 0? That's my question. Next question is, could a1 be equal to 0? Right? If a1 equal to 0, then what do we have? Vieta's formula, right? Sum of the two roots a plus 0 is equal to kb. Right? 0 is equal to b squared minus k. In other words, k is equal to b squared. In other words, a is equal to b cubed. In other words, our left-hand side is equal to, what's a squared? B to the 6th, right? Plus b squared over 1 plus ab, b to the 4th. Extract b square. We have b to the 4th plus 1, right? b to the 4th plus 1, same thing. Cancel out. We have b squared, perfect number, fine. So if a1 was equal to 0, then we're fine, right? We're fine. We're fine. Now, like I said, a1 cannot be smaller than 0, right? Contradiction, we've proven that. However, a1 could be 0. But if a1 was 0, we're fine, right? There's no need to discuss it anymore, right? Already a perfect square. So we can just assume that a1 is, we can just claim that a1 is strictly positive, right? Larger than or equal to 0. But we're already fine with a1 being 0. We're already fine, right? So we only discuss a1, larger than 0. And we'll only discuss this case. So in other words, I've found another root, right? Positive root, except it's smaller than b. Smaller than b, even smaller than a as well. Right? So in other words, I really found, if I just plug a1 into that equation, a1 squared minus kb a1 plus b squared minus k. All right, still makes this equation true. Now I'm going to treat b as a solution, right? I'm going to write b squared as a leading term minus, I'm going to treat a1 as a coefficient, right? Minus k a1 times b and plus a1 squared minus k equal to 0, right? This time, a1 is considered a coefficient, a constant, right? I'm using x squared minus ka1 x plus a1 squared minus k equal to this quadratic equation. We can see that b is a solution, a real solution, right? So b, real solution. In this case, b is bigger than a1. Bigger than a1, right? So following the same method, for this equation, right, a being a real root, I've found another root that's even smaller than b, right? b here plays the role of a coefficient, a constant, right? The same role as a1 plays in here, right? So just a different notation, but same role, same meaning. In other words, here, right? First, a first real root, another real root that's smaller than the coefficient, following the same logic. First real root, another real root, b1, right? Where b1 is smaller than the coefficient, right? Right, following the same logic, right? So first real root, another real root that's smaller than the coefficient, right? First real root, another real root that's smaller than the coefficient. Same logic. Now, in this case, like I said, I automatically assume that a1 is strictly positive because in the case of 0, then we're fine. No need to discuss. Right? So following the same logic, we can automatically assume that b1 is strictly positive. Right? So what I've done now is that I can just plug b1 into this equation, right? So it's a root, right? Plug. So we have b1 squared minus k a1 b1 plus a1 squared minus k equal to 0, right? If I just rearrange it, this term and this term to the other side, I have a1 squared plus b1 squared. And if I just divide this term to the other side and extract k, right? Divide the remaining over. That's 1 plus a1 b1. I'm left with k on the other side. So really, I've found found another pair of positive integers where the same format still yields in the same positive integer, right? The same k, exactly the same k, exactly the same, right? Exactly the same format, right? All right, so here, a bigger than b, we have a1 bigger than b1, right? Exactly the same format. And also following the same logic, I've already reduced a1 and b1 down. I've already reduced a1 smaller than b, b smaller than a1 smaller than a, right? In other words, a1 smaller than a, bigger than 0. Right? b1 smaller than a1, smaller than a1. a1 smaller than a, right? b1 smaller than b. b1 smaller than a1, a1 smaller than b, so b1 smaller than b, right? Strictly positive. Already reduced my pair of positive integers, right? But still strictly positive. And I can following this at the same time, they still satisfy exactly the same condition, right? Exactly the same format, still equal to the same integer, right? Then I can just repetitively do it, right? Like I can find, for example, a2 smaller than a1, right? Bigger than 0. b2 smaller than b1, bigger than 0. Over and over again. Like, for example, an, right, smaller than an minus 1, bigger than 0. bn smaller than bn minus 1, bigger than 0. Where an is bigger than an bigger than bn bigger than 0, right? Always. So I've established a infinite descent now. Is that I repetitively found a pair of positive integers that's always smaller than the previous pair, right? But strictly positive. And each pair, bn is smaller than an. So now the question is that can I reduce? Bn is smaller, right? Can I reduce bn down to 1? Right? My claim is that no, cannot reduce down to 1. The reason is because if for some n, right, so we reduce down to 1, what's going to happen is that we're going to have left-hand side equal just a squared plus 1. Right, so an squared plus 1 over 1 plus an. Right, in this case, I can rewrite it into an squared minus 1, then plus 1, and plus 1. So plus 2 over 1 plus an, right? So an squared minus 1, difference of perfect square, and simplify with bottom. Right, so an plus 1, an minus 1. So an minus 1, an minus 1, plus 2 over 1 plus an in this case. Now, an minus 1 already a positive integer, perhaps non-negative integer. So in order for it to still be the same integer k, we have to require this fraction to be an integer. In other words, we have to require the bottom to be no larger than 2. So in other words, we have to require an to be no larger than 1. So an can only be 1. There's no choice, right? If that's the case, then an and bn are both 1, right? But that's a contradiction. I've assumed a and b are not equal, right? Because if they were equal to each other, k can only be 1. We've discussed that situation, right? So here we assume they're not equal, right? So that's a contradiction already. So my claim is really correct. So like I said, I proved that bn cannot reduce down to 1. So in other words, the minimum possible value that bn can reduce down to is just 2, right? If bn was not 2, then we can keep reducing until it's 2, right? So in this case, what's going to happen? In this case, my claim is that an has to be 8. No choice, has to be 8. If otherwise, right, remember, 8 is essentially 2 cubed, right? If otherwise, if an is any number but 8, in that case, like I said, we have this infinite reduction, infinite descent, only under the assumption that a1 is strictly positive. I've shown that there is a contradiction if a1 was negative, right? So in other words, a1 is non-negative. If a1 was 0, then I've shown that we're fine, right? Turns out to be exactly a perfect square, so we're fine. There's no need to discuss it. So we only assume a1 was strictly positive. So is a2, a3, so is b1, b2, b3, so on and so forth. They're all strictly positive. In other words, since we do not assume any an or bn to be 0, in other words, automatically a does not equal to b cubed, right? Because they're equivalent. Like I said, we've deducted that if a1 was 0, we've deducted a to be b cubed. Right? Likewise, vice versa. So in other words, if everything is strictly positive, then we automatically assumed that a cannot be b cubed, right? If otherwise, it'll be 0, right? So automatically, a cannot be b cubed. In other words, if we say an is not 8, meaning if we say a is not b cubed, right? A is not b cubed, then we can use the infinite descent, right? Infinite descent, like b can continue to reduce, right? Continue to reduce down to 1. Contradiction. Right? Like I said, not equal to 0. In other words, not equal to b cubed. In other words, then we can use, right, infinite reduction. Right? Not equal to 2 cubed. Then we can use infinite reduction. So bn continue to reduce to 1. Contradiction. I've proven that bn cannot reduce down to 1. Right? Contradiction. So an has no choice but to become 8, right? So my assumption, if an was not equal to 8, contradiction, right? So an has no choice but to be 8. Right? Claims, right? So in other words, we can indeed reduce both an and bn until to the point where bn becomes 2 and an becomes 8. It's actually achievable, actually doable. Right? Especially because eventually, right, following the infinite descent, right, even though bn cannot reduce all the way down to 1, but bn can definitely reduce all the way down to 2. Right? Because otherwise, if it were bigger than 2, then we can use infinite reduction again until it reaches 2. Right? It's always doable, definitely doable. And when that happens, then we've successfully shown that an has no choice but to be exactly 8, right? Because otherwise it will be a contradiction. Right? So what I've done is that I've eventually reduced the pair of positive integers a and b, assuming it turns out to be a positive integer. Under this condition, I've successfully reduced both a and b all the way down to 8 and 2, right? While at the same time I've made sure that an squared plus bn squared over 1 plus a and bn is equal to k, exactly the same k, right? So it's true for a1, b1, also true for a2, b2, following the same logic, right? Also true for a and bn, right? Still turns out to be exactly the same positive integer k. Right, so because I've shown that when that's the case, we have exactly a perfect square. So meaning if the perfect square under this condition, then it must be also true, must be also 2 square for a and b, right? Because every time I reduce, I always maintain the same k. Every time, right? From when it were a and b, when it were a1, b1, a2, b2, a and b, always the same k, right? Then eventually we reduce down to 8 and 2. Turns out to be a perfect square. In other words, when it were a and b should also equal to 2 square. So exactly. So indeed, as long as k is an integer, then it is indeed a perfect square. Right? If a and b are not equal, right? If they were equal, then we deduced k is equal to 1.